Okay, in our last segment, we figured out that the coefficient of friction, U, which was our coefficient of friction, the Greek letter mu, and again, we're only talking static over here, staying still friction, was equal to a value of the force of friction static divided by force normal. And generally it's going to be a number smaller than 1. Now, what good is this? Well, that's what we're about to try and show you now. We're going to take the force normal and we're going to do figure out what happens if we start to put this force friction to use by seeing if it's going to hold something on a ramp, for example. Now, there are other segments entitled Forces on Ramps that I've done that we've talked about in class and that you can look at, but I'm going to do it again here and see if you can follow what's going on. Let's create a ramp first of all. Okay. That's a nice ramp, except I don't want it quite like that. Let's take and let's draw one. I think that's probably the best thing to do. Okay, there's our ramp. I want to give this some values. I'm going to say this is going to be 20 degrees over here. It says 20 degrees. Okay, so I've drawn this ramp, and we're going to put some values on this thing. We're going to say that the angle of the ramp right here is 20 degrees. Okay, and as before, we're going to say the coefficient of friction, as we figured out in the last segment, was 0.67. No units on this. And we're also going to say the weight of the block, the force of gravity of the block, which again is equal to the weight, is still equal to 3 newtons. Now the question is this going to slide or not? Well, let's find out. I want to talk a little bit about force normals in case you've forgotten before I go on. And then we'll go back to finding our calculations. Force normals are perpendicular to a surface. Can you see that the force normal in this case is going to come straight up like this? And the force weight is going to be toward the center of the earth, as we've always had it. Now, it turns out that as the force, as you start to tilt the block up at a larger angle, the force normal gets smaller and smaller and smaller. Okay, so we've talked about this in class, but I want to make sure you understand. Let's take a ruler. Okay, and let's pretend that I have this ruler like so, and I have a block on it. There's the block. And I'm going to tell you that at this point, the force normal and the force weight is the force weight of the block. Let me undo that. force weight of the block and the force normal going up like so in a straight line are the same, equal and opposite. Okay, the block is not moving. Now, in my next picture, I'm going to take the ruler, but I'm going to start to tilt it up. Now, the force normal remains as it was before. I'll put the book back on there. Except now it's obviously tilted. Like so. And I'm telling you that the force normal is no longer what it was before. The force normal starts to get a little bit smaller. But the force of the block, the weight itself, pointing always toward the center of the earth, still looks as it did before. So this magnitude right here and this magnitude are the same. Force of weight, force normal. My first example, my second example, and one more example over here, and then I'm going to erase them. I'm going to take the force, I'm going to take that scale, that ruler, and now I'm going to put it way up like this. And my block is now sitting like that. And if I drew my force normals now, the force normal here would start to look very small. But my weight, from the same point going down toward the center of the earth, would be the same magnitude as it was before. The force weight doesn't change. Because you're standing on the side of a mountain, does not mean your weight changes. It only means your force normal changes. And let me do one more thing here. Let's just go one step further. Let's take that same guy and tilt him up the rest of the way. Let's take that block. Let's move him over here. Okay, we've got to tilt them around a little bit more. Now, what do you think is going to happen to the force normal now? The weight is still here. The weight is still the same thing as it was. But now the force normal is no longer there, and this thing is going to free fall. There is no force normal. So you can see here, it started off equal on the force normal is defined as a force perpendicular to a surface. It started off equal to the force of the weight of that block. As we tilted up, the force normal got smaller. And as we went from here to an almost vertical, it got even smaller. And when we went totally vertical, there was no force normal. Okay, so I hope you understand that. I want to erase this now. And go back to our discussion. Let's erase these as well. Okay. So we have a weight of 3 newtons, and we've got 27 degrees. That's all we know. We don't know the force normal, but we're going to find it out. Now, remember on the first, second, and third day of this course, I told you how important trig was? I'm going to redraw this scale, this ramp I'm going to redraw it like this. Okay, so I have redrawn the ramp. I've made it a little coordinate system, as you can see. And in this little coordinate system, I hope you can see that this represents the x-axis over here. This represents the y, and this would be minus x and minus y. And I've tilted the whole thing up at 20 degrees. And on this spot, I'm going to make, on this coordinate system, I'm going to make this spot right here the spot of our block. And we're going to use this as a free body diagram. Now, we've studied free body diagrams, so we know a little bit about what they are. And with a little bit of practice, we will get to be experts on free body diagrams. The next thing I'm going to do is draw the weights that I am aware of, the weights that I know, and put them into this block. Okay, let's start with the force weight. The force weight pulls down toward the center of the Earth. And we're going to label this force weight or force of gravity, either one. Let me put it over here so you know that it's all the same thing. Force gravity of the block is the same as the force weight of the block. So just so we know this is the weight, I'm going to start using Fw of the block, just so you know that that is the force of gravity, which is defined as the weight of the block, and it's going down toward the center of the Earth. Now, as the picture shows, there is also a force normal. And that force normal is going in some direction up. So let's show that as, just as it is in the upper diagram. Oh, pardon me, I didn't want to quite get it like that. Well, I guess I can move it over in a second. Going up like that right on the y-axis. Let me move that over a bit. These are both vectors because they have both a magnitude and a direction. Get it about like that so it looks like the one on top. Okay, so that looks like what we have on top, except we've just put it on a coordinate system. Now the secret to all this is to find the hidden triangle. And this is so important that I'm going to write this down and try and turn it into a game for you. The hidden triangle. Okay. We are going to try, our goal is to find the hidden triangle. And it's going to be a right triangle as well. Now, it turns out, and I will explain this at the end of the slide, it turns out that if this is 20 degrees at this point over here, it turns out this point over here is also going to be, right there, is also going to be 20 degrees. Okay, so far so good. I will explain why in the next section. Now, we know that this force normal, which I will identify up here, force normal, and this is the force weight of the block, and this again is the force normal. You will notice it's not falling through the ramp, which implies there must be an equal and opposite force pulling in the opposite direction. Let's see if we can create an equal and opposite force pulling down here. Okay, that's our equal and opposite force. Since it's a vector as well, let's put some arrows on there. Now, I hope it's obvious from looking at it that the largest force, the largest force is the force of the weight. Everything else is less. Therefore, this is going to become a hypotenuse. The force normal is less. We started to tilt up and that force normal gets smaller and smaller and smaller. It starts off even, but as soon as we're on the ramp, remember the last section? It gets smaller and smaller and smaller the steeper the ramp. So, I'm going to put a red line across this because now I want to show you that this creates, going up in this direction right across, a right triangle. Let me explain where most people make their mistake. And I'll do that by erasing this. I want to make that a little neater anyway. Let me go back and let's put the arrows back on here because this is a vector. Let's do it in black. Force normal is a vector. And what I'm going to do now is I'm going to try and draw a line straight across like this because this is going to be our right triangle. And I want to do it in, let's try and do it in purple. We'll see what happens. There it is, right across. Our 90 degree is right at this point. This is the hypotenuse. This is the adjacent of a right triangle. This is the opposite. Okay? Where most people make the mistake is right here. They take, and let's do it in a different color. Let's do it in orange. They take and they come straight across like so. Okay? And they say this is the 90 degree at this point, and this all of a sudden they stretch to make the hypotenuse. But we've already agreed that the force weight, force of gravity of the block, which is equal to the force weight of the block, is the largest portion of the right triangle. And it is therefore equal to the hypotenuse. Everything else is smaller, but if you make this line go straight across like this, okay, just like that, you've made, I hope it's obvious, you've extended unnaturally, incorrectly, the normal. So instead of having a triangle that looks like this, let's see if I can do this. Instead of having a triangle that looks like this, oops. Okay, there's one side. I'm exaggerating a little bit. You've got a triangle that looks like this. If you make that mistake, look at the difference. On this side, this was the hypotenuse. When you do it incorrectly, you change the hypotenuse from here to here. Okay, are we clear on that? All right, let's keep going. Let's get rid of this. Okay. And since I already kind of gave it away that this is the triangle we're looking for, this is going to be, this right triangle here is our hidden triangle. And this side I'm going to redraw in orange over here. Well, I think I chose red instead, but that's okay. We'll use the red. Now, it turns out that this is the same magnitude as I would have if I moved it from here to here. Let me get rid of the, let's make it the purple. Let's get rid of this guy down here. And as a matter of fact, let's take this out and let's keep it as the purple. And I want to show you by moving it. This side over here is a magnitude. It's another force. And that force is the same. I can take this force and move it right up to here. So these are the same forces. Can you see that this makes a rectangle here? It's a rectangle. And this force going down okay, I want to redo that a little bit. We have got a force. We've got a side of this triangle that looks like that. Okay. Can you see this and this are the same? And altogether, this whole thing forms a right triangle here and an inverted right triangle here. It's really a rectangle. Well, it turns out that this opposite side right here, the side right here, the opposite side, this guy right there, the opposite side, don't forget this is the adjacent, because here's our angle of 20 degrees over here, that the opposite side is the sliding force. We're going to call that the force sliding. Fs equals sliding force. That's how the block wants to go down. Okay? And we're not sure, in fact, if it's really going to. The only way we know for sure whether it will or not is if we know what the force of friction is. Now, I'm going to show this force of friction a little bit different than I did before. I'm going to show the force of friction. See, we're not pulling it now. Gravity's trying to let it slide all the way down. So we've just added a force sliding that looks like this. And if it does not slide, it must mean that there is another force pulling up over here that's holding it. And this will become our force of friction static. Before it was working to hold it back from the pulley and weight, pulling it this way. Now it's trying to hold it from the friction, from the gravity, trying to pull it down that way. So the force of friction can be either way. Now, if we know which is bigger, this one or the force sliding, then we'll know if this thing is going to slide or stay still. So let's summarize. Down here on the bottom, this will become our force sliding. Okay? And we've got to determine what the force friction will be going in this direction up here. That's going to try and hold it. Well, how are we going to do that? Well, how do we find the force of friction static? Well, let's clean this up a little bit and maybe we can see. Wait a minute. We have a mu. We calculated it the first time. Remember, mu has no units, and it's a relationship between the force of friction static and the force normal. Yeah, but we don't know what the force normal is. We used to when it was on a flat surface, but we don't know what it is now. But wait a second. If we've got 20 degrees here, let me clean this up a little bit. Oops, wrong color. If we know the angle right there is 20 degrees, and we know one side, which we do, because in our last segment we said that the weight was equal to 3 newtons, and that doesn't change regardless of the slope, then we could find either of these sides. And if we know what the adjacent side is right here, this guy pulling down right here, then we will know what the force normal is because it's the opposite. Remember, this block is not sliding, falling through the ramp, so it must be staying still. So let's see if we can find out what the adjacent is. Well, turns out that the adjacent, and you know this already, is equal to the hypotenuse times the cosine of the angle, SOHCAHTOA. Well, if the hypotenuse is 3 newtons, all we got to do is multiply it times the cosine of 20 degrees. Okay. Okay. So that would be 3 times the cosine of 20 degrees is going to be equal to 2.81. So let's just put that over here. Is equal to 2.81 newtons. That seems like a reasonable value. Here's the hypotenuse. It's smaller than the hypotenuse. I think that's a reasonable value. So we're going to say the adjacent side is equal to 2.81. And therefore, newtons, and therefore, the normal is equal to 2.81. Okay, so now what? Well, let's see what happens here. It says that we have the coefficient of friction equal to 0.67. Okay, and if I cross multiply, we can find out that the force of friction static is equal to mu times the force normal, which is equal to 0.67 times 2.8 newtons. Okay. That's 0.67 times 2.8. And I got 1.88 as an answer. So let's put that down, which is equal to a force of friction equal to 1.88 newtons. Okay, I'm going to put that right in. The force of friction equals 1.88 newtons. And I'll put it in over here too. It's equal to 1.88 newtons. That's what's trying to hold it back while gravity is trying to slide it in this direction. Okay, well, if we got 1.88, I wonder what the force sliding is. Well, let's do that next. Let's find out what the force sliding is. And we can do that by finding the opposite. Well, the opposite is equal to h times the sine of 20 degrees, which is equal to 3 newtons times the sine of 20, and let's see what happens. Let's get the calculator back up. 3 newtons times the sine of 20, I get an answer of 1.03. So this is going to be, for sliding, is going to be 1.03 newtons. That's the opposite side, 1.03 newtons, which makes this 1.03 newtons, trying to pull it back down, which is the same as this over here, 1.03 newtons. And we got 1.88 pulling it up. Well, who's going to win this battle? If the largest amount we can get is 1.03, let me clean this up a little bit on this side. .03 newtons, and the other side can hold back with 1.88. It looks as though this thing is not going to slide. Now I know this looks a little complex, but with practice for several of them, you'll be able to get it. I think that if you look at the other tutorials as well as this one, it'll start to become clearer and clearer. But we'll do plenty of these in class to try and get the idea. So back to our original problem, we tried to find out, based upon how this object slides, we had to find a mu. Let's clean this up and see what we have. Our original problem was to find mu, and we said mu for static was equal to the force of friction static divided by force normal. And what we did then is we had a ramp, we had a table, and on that table, okay, we put a block. And also on that table, we had a pulley. And the whole point was to put a rope around that pulley like so, and I'll move that pulley down a bit. And by putting a cup on the end of it, we were going to figure out when this thing started to slide. It's not quite the same cup I had before, but that's okay. You get the idea. We're going to take this cup and fill it with pennies over here until it just started to slide. Do you recall? Okay, and when it started to slide, we would note this force of gravity of the cup. We would note that force of gravity of the cup. Okay, And we knew there was a force normal over here as well, but we weren't going to do anything with it for a while. There was a force normal pulling up, and that force normal existed because there was a force of gravity pulling down. Okay, and it was not sliding through the table, punching through the table, so we knew that the sum of the forces, because of Newton's second law, must be equal to 0, because there was no acceleration. All right, so we put the pennies in the cup, and it just started to move, the cup. As soon as it started to move, we knew at that point that the force of friction could not keep up with the forces in the cup. We knew that the force of friction going this way just could not keep up, and we noted that that last penny that we added was the one that broke the camel's back. And we said, aha, based upon that, the force of friction static was equal to the force of gravity in the cup. That's where the force of friction static just couldn't hold on anymore. And we said, that's great. And we went back and said, well, in that case, if we knew the force normal, and we did because we said this weight was going to be equal to 3 newtons, that would make the force normal equal to 3 newtons, then we could figure out the force of friction static, because we pretended that we knew that this was 2 newtons over here that caused the object, the block, to start sliding in this direction. So we plugged it in and got 2 newtons over 3 newtons, which was newtons cancel. There's no units here. And we had 0.67 as our mu. Now I took the whole thing and put it on a ramp. We now had everything we needed. We knew the mu, and we said, okay, could we possibly figure out if something is going to slide when it's on a ramp? And we said, we drew a ramp. We said, okay, first of all, let's get a ramp. And we drew that ramp up like so. And we said that ramp was going to have an angle of 20 degrees. And we said this was 20 degrees right here. I then said, okay, I'm going to redraw that as a coordinate system. Okay, and I know it's different colors, but I said here was our coordinate system. The x and the y. And I said in the center of that coordinate system, I was going to make my free body diagram in red right here. And I said that I knew that no matter what, the force weight was always going to be the biggest vector in this thing, and it was always going to be pulling down toward the center of the earth. And I also said that the force normal was always going to be perpendicular to a surface, and I drew it, oops, let me undo that. I drew it as a line going up. Let's make a line right here. And it was always the biggest this line could ever be is on a flat surface. It would be equal to the force of gravity. That's the best it could ever be. And I said, but as you start to tilt, the force of gravity gets smaller and smaller and smaller. So it stands out. I'm going to put the top of this right here. And remember, this was 20 degrees right here. And I told you that we had, our job was to find a secant triangle. And since we know that the force weight is the longest vector on this triangle, I was going to, and I'll show you later, I told you that this was going to be where the 20 degrees ended up. And our job was to find the hidden triangle. And I said there were two ways to do it. Most people make the mistake of drawing that line straight across, okay, which makes this part the longest side, and this is incorrect. I said what we wanted to do is make a right triangle with the force weight being our hypotenuse, and that would make this the right triangle like that. So let's erase this, and that became our hidden triangle. And the next thing I told you was that this green was actually going to end up being our force slipping. Force of that block trying to slip down the ramp. And we could take it and move it right to here. Same magnitude, same direction. Now, can you also see that this is also our opposite side from our triangle, meaning this side would become our adjacent, and that was our hidden triangle. Now, it's also important to realize that the adjacent here was also going to give us the value for our force normal right here. So everything is set, all the information we want seems to be centered around this triangle. Now, why do we need the force normal? We need that force normal because we've got to find the force of friction static. And in order to find the force of friction static, we need the mu, which we already have. It won't change. It's independent of the shape of the ramp. And we need the force normal. But we don't have the new force normal because we are tilted now. In order to find the force normal, we need this triangle. Okay? And when it turned out, in the last slide, you can look at the numbers, we found out the adjacent and the opposite, and this became our force slipping over here. Let's go back to a green. This became our force slipping. We had the force normal, and we plugged in our force normal into this equation. We got our force of friction static, but now we said the static was pulling in the opposite direction. This force of friction static was now not trying to hold it back from the pulley, but trying to stop it from sliding. Okay, I'm sure you're going to have plenty of questions on this, and we're going to do several problems in class. But this should, based upon doing the practice in class and looking at this several times, you should start to get an idea of how to find the slip angle on a ramp. And just for practice, let's pretend, go back and take all the values you have, and say now, what if the angle was 40 degrees? So change this to 40 over here. And see if it would now slip. Oh, I was going to show you how the ramp ends up being 20. How this 20 degrees along the ramp tilt ends up being 20 over here. Let me show you that. Okay, we still have our force going down toward the center of the earth. Our force weight, that is. And here is our ramp. Here is our ground. And at this point right here, the red dot is equal to 20 degrees. Can you see this makes a 90 right here? Another right triangle. What's the total number of degrees in a right triangle? I hope you said that in a triangle, 180 degrees is the total number of angles. Well, if this is 90, 90 plus 20 is 111. What does that have to make this? That has to make this angle over here 70 degrees. Can you also see the blue over here is a total of 90? It's a right triangle. It's a 90 degree right here. Just as this is 90 degrees, this is 90 degrees, and this whole thing over here is 90 degrees. Well, if part of this is 70, the only way we can get this blue section up to 90 is by making this 20. And if I take this portion out, I take everything out now. If I take this guy over here, and if I take this guy over here, I'm trying to recreate my right triangle. Actually, I don't want to do that. Let that stay there, and we'll put this back. I'm just gonna take this, and if I know that the hypotenuse has got to be the longest side, then this becomes our right triangle. Let's see if I can color that in. I don't know that I can. This becomes our right triangle. I don't like doing it that way. So we got the 20. Let's clean it up. And let's do it in a nice purple again. We'll stick with purple. This becomes our right triangle. And now let's try coloring it in a bit. Here is our hidden triangle. And now we just use SOHCAHTOA to figure out all the sides. Knowing that, when we're done calculating the values, that this becomes this vector, and the other side, let's give it a purple just so it stands out, this other side over here becomes the value, the magnitude of the normal up here. Okay? I hope this helps. Oh, also, by the way, let me clean this up. I hope you know enough about vectors now to see that that weight is really made up of two guys pulling in the direction shown. One guy pulling like this, it's one vector, and the other guy pulling down like this. It's these two let's see if I can clean this up a little bit. It's these two that form the two vectors that create the weight. Well, I hope this is helpful. I know it was kind of long and drawn out, but go through it. Take your time. Take as many lessons as you want. Take as many times as you want to look at it, and see if you can make any sense out of it.